Direct, inverse, and joint variation. Let us start with direct variation. Direct variation is a linear relationship between two variables. So we might have a scenario that says y varies directly with x. When it's presented like this, y is varying directly according to the value of x. So y is your dependent variable in the function you're trying to write, and x is your independent. And because it varies directly, we know that there's a linear relationship. So we're going to say y, being our dependent variable, equals some linear function x. Now, how y varies is going to be dictated by some constant k. And that constant k is going to be in that same position that your slope would be in a linear function. So we should notice that this function is in our standard form for a linear equation, which is y equals ax plus b. That's your standard form linear equation, and it is reflective of that. Now, let's make a note that k is a constant. It's not going to be a variable. And it can't be equal to 0. In the event it's equal to 0, then there's no variation or no relationship. So now, there's your direct variation formula. We should also note that in a certain scenario, when k is greater than 0, we have this nice relationship between the x and the y variable. As x increases, the y value will increase. And as x decreases, then y will decrease. So maybe I'll add that terminology so it doesn't look like then. To look at some real life examples of direct variation, we can look at two familiar equations. First, let's look at a more basic one, circumference of a circle, 2 pi r. We can see this is in the same structured format as our general direct variation function. The 2 pi is your k, that's your constant, and then your r, your independent variable, and the circumference is your dependent variable. Same linear function. This is a linear equation. And we can see that our k value is greater than 0. So we expect when the radius of the circle increases, the circumference increases. And that should make sense. When the radius of a circle decreases, the circumference decreases. So that's one example of a direct variation function in real life. And the other, how about we look at the force equation, mass times acceleration. Now, we do have two variables off to the right, mass and acceleration. They could both theoretically change. But if we held one to be a constant, let's say we have some object where the mass does not change. So if we keep this constant, then we do have that linear function relationship between acceleration and force, where force varies directly with acceleration. And because mass of an object will be greater than 0, it should also make sense that if we increase acceleration, the force will increase. Or if we decrease the acceleration, the force will decrease. But we don't just have to hold mass constant, we could hold the acceleration constant. So if we're moving at a constant acceleration and the mass changes, so if the mass increases, then we'll have an increase in force. But if the mass decreases, we'll have a decrease in force. So there is a direct variation relationship. If I hold one of those variables constant, we now have a linear equation. And before we move on to inverse variation, when we look at the function y equals kvx, k times x, not k to the x. If we manipulate this equation, knowing that k is a constant, if we solve for k, we're going to get y over x. What this reveals to us is a way to determine whether or not a set of points indicates we have a direct variation between the two variables. Direct variation will have a constant ratio between the variables. So that is what that tells us. If we want to identify direct variation, we're looking for a constant ratio between quantities of x and y. Moving over to inverse variation. If we say y varies inversely with x, y is still the dependent variable, x still the independent, but instead of a linear relationship, we have this reciprocal relationship. So instead of it being k times x, we want k times the reciprocal of x, which is 1 over x, which is going to look like k divided by x. So the inverse relationship implies a reciprocal nature in the function. This function is a rational function, which is what this unit is all about. So here's our first introduction to this type of function. Now, k is still a constant. And cannot equal 0 because the whole quantity would be equal to 0. But x cannot equal 0 either now because if it did, we would have an undefined expression. In the event that k is greater than 0, then this time when we increase x, the value of y decreases. So what you'll see is you'll have some constant value k, and imagine the denominator keeps getting larger and larger and larger. The overall value gets smaller and smaller and smaller of that ratio, and that ratio equals y. So y is going to go down. Or as x decreases, if x gets smaller and smaller and smaller, the overall ratio value will go up. So there's an inverse relationship between x and y. One example to look at would be speed. Speed is equal to distance over time. Now, distance and time are both variables, but we're showing this example in the event that we hold distance constant. So we have a set distance we're trying to travel. In the event that it is held constant, we now have an inverse relationship between s and t. We could say speed varies inversely with time. And because we're going to have a positive distance that we need to cover, we can see that if we increase the time, then the speed will decrease. So if we increase the amount of time we're going to use to cover that distance, the speed in which we're traveling will go down. So increase time, s goes down. But if we decrease the time it takes to cover that distance, we expect speed to go up. And that relationship should be flipped. If you increase the speed, the time goes down. If you decrease the speed, the time goes up. So that can be shown through a manipulation of the equation. If we multiply both sides by t and then divide by s, we could flip that equation to show that t also varies inversely with speed. So either way, we see that increasing one decreases the other, or vice versa, when we hold the distance at a positive constant. So there's an application for an inverse variation relationship. And to end the inverse relationship talk, let's look at the function, the general function. If we solve for k, this will be a way to identify when we have an inverse relationship given a set of values for x and y. With the direct variation, we saw that we had a constant ratio. That is how we identify direct variation. Now we're going to notice that we have a constant product. And if you confuse the two, just remember that this is found by solving for k. That will reveal how you can identify inverse versus direct variation when given a set of points. So constant product for inverse, constant ratio for direct. Now let's jump over to joint variation. Joint variation is going to be a relationship between three variables. So we'll have y varies jointly with x and z. This is a case where we have y equals, we'll have some constant k, because we don't know how y is going to vary, times x times z. So k is our constant, cannot be 0. Now, what's an application for the joint variation? Maybe the area formula for a rectangle, where the k value is equal to 1, because our area formula is base times height. So we see a relationship between three variables here, and it says a is going to vary jointly with the base and the height. Now, if we hold the base constant, we increase the height, the area goes up. Decrease the height, the area goes down. So there's still that direct relationship where if you increase one, the other increases, assuming that our constant is greater than 0. But in an area application, we're obviously going to have lengths that are positive. So there's an example of a joint variation where we have a relationship between three variables. This is the general formula for joint variation. So you will see y varies jointly with x and z. So both x and z are independent. We can vary them as we'd like within the context of the problem, and y's value will be dependent on that. Now, identifying joint variation, you'll see if you solve for k, we're going to have something like this. So it's not necessarily, we have a constant ratio, but we have a product in that denominator. But we don't have to focus on that. What I wanted to just bring up is the joint variation general formula. So just know that terminology. If you see something varies jointly, you know three variables are involved, one of which varies with respect to the other two. And we have this product of the two independent variables with the constant k. In a real life example, area formulas of a rectangle, or even area formula of a triangle, where we do have a k value other than 1, be 1/2. So there are some examples there. And then to end the video, we're going to look at a combined variation. So what if you have something that's varying directly with respect to one variable, but inversely with respect to another? So if we have y varies directly with x and inversely with z, how do we format that general equation? So what if we have a scenario that's telling us something like this? Well, we're going to say y is our dependent variable. Let's handle the directly first. We're going to say k times x. That's our general direct variation function. But then if it's also varying inversely with z, then all we have to do is divide by z to show the reciprocal nature with z in its relationship with y. So this is your general formula for a combined variation if you have directly with x, inversely with z. K is still your constant. And cannot equal 0, but z in this case could not equal 0 as well to avoid an undefined function. So just to take a look at that combined, how that would work, we'll do a quick example. Let's say the volume of a gas varies inversely with the pressure and directly with the temperature. So volume of a gas varies inversely with the pressure and directly with the temperature. So volume is our dependent variable. It varies directly with the temperature and inversely with the pressure. So there's your volume formula for a gas. Then it says a certain gas has a volume of 10 liters, a temperature of 300 kelvins, and a pressure of 1.5 atmospheres. Now, just knowing that, that is what we call the initial condition. So in a lot of these problems, whether you're doing joint, inverse, direct, combined, They give you some initial conditions so that you can find the constant K. So in this problem, when they tell us the volume is 10, the temperature is 300 kelvins, and the pressure is 1.5 atmospheres, that piece of information is what we call the initial condition. And what we'll make a note of is the initial condition allows us to find the constant K in any of these variation problems. So I know we're only doing this one example, but it combines both the direct and inverse, so we can kill two birds with one stone here. But just know there's going to be an initial condition given. That's how you find K, because they're not going to give you K. So now that we know that, let's find K. So we'll say 10 equals K times 300 for 1.5. If we multiply both sides by 1.5, we'll get 15 equals K, 300. Then if we divide by 300, we will get 0.05 for K. Now that we know K, we can write the volume for the gas that reflects this initial condition. So by putting in 0.05 T over P, this is our function that models this scenario. So if they ask you for the function, they're asking you to find the K value based on the initial condition and then write the general function off of that. Now, once we have that function, it then asks us if the gas is compressed to a volume of 7.5 and heated to 350, what will the new pressure be? So if we know that volume is now 7.5, so they compressed it down from 10 to 7.5. We know the constant and the temperature went from 300 to 350. What is the pressure? So now we can solve for P. If we multiply both sides by P and then divide by 7.5, we get 0.05 350 over 7.5. We can make that calculation to get our pressure. So there's an example of a combined variation where it has both direct and inverse within the problem. We had to find a value K from an initial condition. Once we have K, we can write a general function. And again, this goes for any type of problem in this section, whether it's direct, inverse, or joint. You handle it the same way. Then we can use that function to find missing pieces when we know values for the other variables. So that's where we will conclude this video.